we're going to cover as much as I can today, or well, I say that I might run out of material because I didn't get to finish all of the notes that I wanted to on frequency compensation. But my expectation is that we will talk today up until a certain point, and then we will have a short half-hour tops-ish thing on Friday, maybe do a little bit of more work on electric, and then we are done. Okay.
So the things that are left to turn in are homework 3 and homework 2.
Yeah, and there will be a homework 4 that is literally just going to be our differential stage chained into our output stage with compensation network put in there as well, which is what we're talking about on Friday.
Okay.
Like what the compensation network entails is going to be a capacitor, but I'll explain exactly why it works and all of that kind of stuff over the next few class meetings, the next 2 class meetings, very specifically, actually. All right, so we have a differential stage that is designed, right? So here is our supply voltage VDD. We have, that should be drawn the other direction. So this is transistor M3. Here is transistor M1, at which we apply one of our input voltages. Effectively mirroring this. Here is M2, where we apply our second input voltage, VN2. Here is M4. I don't know why the M didn't write. And there's our output terminal. And then down here, we have a tail current source. I'm drawing it this way, but we know that this is effectively a cascade current source that's connected to our bias network. So I'm just going to write 2 bias network out this direction, because everything here is independent of our bias network. Okay. So this is where we are at effectively in our design. Now we're going to move along to the next stage. Okay, so we have here a differential stage. And according to our simulations, we get a gain of roughly, I think it was 23 volts per volt, which anything above 20 for a single differential stage like this is actually quite good. So now we're going to talk about our gain stage over here. This will be fairly brief, and then we're going to loop it back in with our frequency response. Okay, so our gain stage is going to be this guy. Here is VDD. We are going to have a PMOS transistor. And I'm going to put a circle here. So the output node of our differential stage or our single stage op amp is going to be the input node of our gain stage. Down here, we are going to have an NMOS transistor. So effectively, we're biasing this with a current source. We could potentially replace this with effectively a cascade amplifier stage if we wanted to, but for simplicity's sake, let's just leave it a single transistor gain stage. And then this is our new output node that will in turn chain into our output stage, which I think we're going to run out of time before we really get into any detail about that. Okay. So our overall system gain will be of the form, our differential gain multiplied by our gain stage gain. But both of these quantities are actually frequency dependent. We dealt with the frequency dependency of our differential stage in class on Monday, because today is Wednesday. Does that sound right? Yeah. So today we're going to briefly go through the frequency response. Sorry, I had a brain fart there. The frequency response of our gain stage, what implications that has on the frequency response of our differential stage. And then from there, get more into the nitty gritty of what's going to happen once we apply negative feedback to this thing. Okay. So first, just for the pure sake of argument, what kind of amplifier is our gain stage? Common source. Absolutely right. Common source amplifier where the PMOS transistor, so let's call this, my screen would stop sliding away from me, MCSP, and this guy will be MCSN for common source PMOS transistor and common source NMOS transistor. These are not, the CS here doesn't stand for current source, even though the NMOS transistor is behaving like a current source. Anyway, just wanted to clarify that. So if we want to look at our frequency response of just our gain stage, let me put a circle around it. We're focusing principally on this. We're going to look at the small signal model. I'll put that here. So this ground up here at the top represents what's going on at VDD. So this is going to be the source for our PMOS transistor. Here is GMP, VSGP. Here is R0P. This is where our voltage VSGP is. This is our gate for our PMOS transistor. And here is where our input voltage for this stage is being applied. And this is the drain of our PMOS transistor here. Down here, I'm going to draw the small signal model for my NMOS transistor. So here we're going to have GMN, VGSN. This is going to be in parallel with R0N. Here is VGSN. This is our gate for our NMOS transistor, and because we are applying a DC bias voltage at the gate, this is going to look like AC ground. This node, our source for our NMOS transistor, is also at AC ground. This is our drain for our NMOS transistor, and here is our output node, which I am just going to call node Z for right now. So this is what our mid-band model would look like, because this one isn't going to be as terrifying as what we were dealing with on Monday. I'm going to go ahead and include our high frequency capacitors, and we're going to figure out how this thing works all in one shot. So I'm going to put my high frequency capacitors in purple. So this guy is going to be CGSP. This guy is going to be CGDP. This guy is going to be CDBP. And similarly, I will have a CGSN, a CGDN, and a CDBN, like so. So before we get to analyzing things here, does anybody have any problem with our small signal model? All right, so a couple of things that we can note is that since the gate of our NMOS transistor, excuse me, and the source of our NMOS transistor are at the same potential, CGSN is shorted out and does nothing. VGSN as a quantity is also 0, which means this current source behaves like an open circuit. So from here, we can see fairly easily that the resistance seen at node Z or between node Z and ground is just R naught P in parallel with R naught N. No other resistances. Everybody okay with that? All right. The capacitance seen at node Z or between node Z and ground. So we have CDBP directly between node Z and ground. And then we have CDBN directly between node Z and ground. We have CGDN directly between node Z and ground. And then we're going to have CGDP, and I'll put an asterisk in red, much like I did on Monday's class, because this is a Miller capacitance that is referred to that output node, okay? So I'm going to make a note here as well that we are going to have some capacitance that is referred to the input node. That is going to be effectively a Miller capacitance associated with CGDP as well, but we won't know what that is really until we figure out the transfer function of this thing so that we know what the DC gain is, and then we can refer some portion to the input. All right, so a couple of things here. Our input voltage Vin by inspection is negative VSGP. Everybody see that? So the negative polarity terminal of VSGP is associated with the positive polarity terminal of Vin. The positive polarity terminal of VSGP is effectively at ground source, and the negative polarity terminal of Vn would be associated with ground. So they're equal and opposite voltages. So that's going to allow me to redraw my circuit. So here I have GMVN, and it should be oriented down, the current flowing towards ground effectively, in parallel with RZ, in parallel with CZ, and then here is our output voltages polarity. And so from this, start up here, we can see that V out is going to be negative GMP, excuse me, times VN times RZ in parallel with 1 over SCZ. And using that little thing that we derived on Monday, this is going to look like, actually, we'll just do this directly. The transfer function. Have we used a symbol for a transfer function in this class? All right. Have I called it H or A or blah, blah, blah? H, okay. So H as a function of S, where this is going to be a complex number, is going to come out as negative GMP R naught N in parallel with R naught P multiplied by a factor of 1 over 1 plus S R naught N in parallel with R naught P times CZ. So this is our frequency response transfer function. Okay. Where I've taken, so just to be really clear here, whenever I have R in parallel with 1 over SC, this becomes R over 1 plus S RC, and then just use that relationship directly there. Okay. This quantity right here is our mid-band gain. And then the quantity to the right side tells us effectively where our pole is going to be. So we could say that our pole, unsurprisingly, is going to be at 1 over RCCZ. All right. So before we move along to bigger and better things, let's talk very briefly about the capacitance that's referred to the input and why this is going to be important. So when we looked at the differential stage yesterday, we didn't mention any capacitance referred to the input whatsoever, although we used Miller's theorem to split up multiple feedback capacitors, so there should have been a capacitance associated with each of those input terminals. What was the resistance that we would have seen at each of those input terminals? Infinite, which means our pole frequencies associated at either of those input terminals would have been infinitely high, and therefore they're not actually going to contribute anything to our overall frequency response. Okay. Now, we don't see any resistance associated with the input terminal of this stage, but we know very definitively there was a resistance at the output of our previous stage. So effectively, this Cn that we are going to find is going to get lumped in to the Cy that we determined in Monday's lecture. So it will have some influence on the behavior of the frequency response. Since it's serving to make Cy larger, it's making our output pole of our differential stage more and more dominant. It's pushing it closer and closer towards, it's making the frequency lower. So it's creating separation between the subsequent pole that we saw. Okay. So using Miller's theorem, C in here, which is going to get added to Cy, is just going to be whatever CGDP is times a factor of 1 minus our DC gain, but since our DC gain is negative, this is going to look like 1 plus GMP R naught N in parallel with R naught P. So we are making CY larger, and not just by a factor of CGDP, but this is getting multiplied or scaled by what should be a fairly appreciable amount if our gain stage has a high gain, which is literally what it's designed to do. Okay. So we're referring some portion of this capacitor here to the output of our differential stage, thereby making that CY even larger and pushing the location of that pole closer towards 0 hertz or 0 radians per second. Okay. Understanding the influence of this capacitance is going to come into play when we talk about intentionally compensating things. All right. So now that we understand what's going on here, hopefully we all understand that our overall transfer function for this guy is just going to be our 2 transfer functions for each stage multiplied by each other, so that now we have a system with even larger gain in magnitude because we have the gain of the first stage, or the DC gain of the first stage, multiplied by the DC gain of the second stage. And then we're also going to have a multi-pole frequency response because we have the frequency characteristics of the first stage being multiplied by the frequency characteristics of the second stage. So now let's talk about negative feedback. We're not going to go through the huge multi-day derivation or anything like that we did in 336. We're going to consolidate things. And so let's see, negative feedback. And frequency response. Okay. All right. So in order to use an op-amp circuit for its intended purpose of linearly amplifying signals, we, in all of our previous experience dealing with op-amp integrated circuits, have done what? Employed negative feedback, right? That's what those resistors that we connect to our op-amp circuit do. Specifically, we always have some resistance placed between the inverting input terminal and the output terminal, providing literally negative feedback. And then the role of the other resistor, depending on the type of amplifier that we have, can be thought of as that's getting beyond the scope of the course. Effectively, if we want to make our amplifier actually capable of linear amplification, not rail-to-rail outputs oscillations, we need to employ negative feedback, okay? We discussed in ELN 336 that negative feedback offers a multitude of advantages. So let's briefly talk about those advantages. Advantages. So they were, in no particular order: lower sensitivity to process variation, improved noise rejection, increased linearity, and improved input-output characteristics. there was one other thing, and we're going to talk about that in a moment. What is the arguable disadvantage or con of negative feedback? It's really only one.
Picture signal makes it negative.
Nope. Lowers the gain. So how negative feedback affects frequency response is literally a one-to-one trade-off. Okay. So we learned in electrical engineering 336 that if we decrease the gain of our system by employing negative feedback, so if we have some gain with feedback, AF is equal to A, our open loop gain, divided by 1 plus KA, where just for nomenclature's sake, KA is the loop gain, 1 plus KA is the amount of feedback. We found that our bandwidth with feedback was our bandwidth without feedback scaled by a factor of 1 plus KA. This is true particularly for a single pole amplifier circuit, okay? One consequence of this, and we talked about this very briefly this concept very briefly on Monday, is that this results in a constant gain bandwidth product. So if I multiply my gain with feedback times my bandwidth with feedback, I get A over 1 plus KA times my bandwidth without feedback times 1 plus KA. The 1 plus KA terms cancel each other out. And my gain bandwidth product with feedback must be identically equal to my gain bandwidth product without feedback. Okay. We're also going to call our gain bandwidth product here. So GBP is therefore A times BW. So gain, open loop gain times open loop bandwidth, which is the same as closed loop gain times closed loop bandwidth, is going to be omega T, our transition or unity gain frequency. This guy's going to pop up again, so I'm going to note that. Okay. So if we look at a Bode plot for a single pole amplifier with feedback and without feedback, so here's AV as a function or expressed in decibels. Here is omega. If this bottom bit corresponds to 0 dB, and this guy right here corresponds to the magnitude of A, our open loop gain in decibels, we should expect a response curve something like this. Goodness gracious. Where when our gain response hits 0 decibels, we are at our transmission or unity gain frequency. And this frequency right here corresponds to the location of the pole for our single pole amplifier. When feedback is applied, let's say that this point here corresponds to what the magnitude of our gain with feedback is. What we will see is that our gain is reduced until we hit our pole frequency, at which point it effectively rolls off. And everything beyond the pole matches up perfectly. So this is our new omega p with feedback. And we can see then that our bandwidth has been extended. You guys have hopefully seen these curves numerous times looking at data sheets for op amps and all of that kind of good stuff. Now let's look at what happens with our phase. So I'm going to draw a phase diagram here. A little more than I needed, but it'll be okay. So this is going to correspond to an angle of 0 degrees. This is going to correspond to an angle of -90. So this one is going to be -45 degrees. Down here, although we're not going to use it, is -135 degrees. And so what we should see without feedback is that at a frequency of approximately 1/10 of omega p. So actually, let me specify something here. This is a log of omega graph. So what our frequency response plot is supposed to look like is effectively at omega p. At this very specific frequency, we're going to hit -45 degrees. At 1/10 of omega p, it's going to start changing from 0 and heading towards that -45 degrees. And at approximately 10 omega p, or 1 decade further, we are going to hit -90. So the single pole amplifier is going to introduce overall a 90-degree phase shift. It's going to look something like this. Okay. And let's call where we start to transition here 0.1 omega p, and where we hit -90 degrees, 10 omega p. And our omega p, again, is a frequency where we hit exactly 45 degrees. Well, if we increase the bandwidth, we are increasing where the location of where our phase starts to change, right? So instead, now, just going to put dashed lines down here. So this point here is where we're going to hit 45. So if that's where we start to transition, it's going to look something like that, right? So the application of negative feedback plays a role in both the magnitude response and our phase response. And this is critically important, especially when we have multi-pole amplifiers. Okay. So let's look at something here. Our basic transfer function diagram for an amplifier with feedback. We have our signal that we're trying to amplify, X sub S. It goes into a summer. Here is our actual amplifier stage. A as a function of omega. Over here, where we're going to take our output, Y. And then when we have a feedback network in place, which can also be frequency dependent. Did we use K in 336? Capital K for feedback factor?
Yes.
Okay. I'll label stuff just in case in a moment. Here is, so this is supposed to be representing a negative feedback system. So this is XF. And this is our error signal, XI. And our transfer function, so our gain with feedback as a function of omega should be A of omega, where that represents our open loop gain as a function of frequency, times 1 plus K omega A omega. Our general form, okay? So for a single pole amplifier, the quantity K omega times A omega literally can never be negative, because the most phase shift that we could ever achieve is 90 degrees. If we have a multi-pole amplifier, there may be a specific range of frequencies over which our loop gain, K omega, or K of omega times A of omega, becomes negative. What happens if our loop gain becomes negative? We no longer have negative feedback, we have positive feedback, and our system is no longer stable. So that's where all of this stuff that we're talking about is going to come in, okay? So effectively, for every pole that our amplifier has beyond 1, we are introducing the possibility of system instability. Okay. All right. So that brings us to a brief discussion on system stability. I happened to glance at the board of what was going on in controls. I think it was earlier today, where you guys were talking about frequency responsive control systems. It's very likely that you talked about this literal exact same topic today. So sorry that you're going to be bored, but it is what it is. Okay. So for a single pole system, the maximum phase shift that can occur is 90 degrees. And so these systems are effectively unconditionally stable. In a multi-pole system, the maximum phase shift will be greater than or equal to 180 degrees, and the system risks becoming unstable. This risk can be summarized by a plot in the S-plane diagram. So here is our S-plane diagram. Like so, where the horizontal axis corresponds to sigma, the real part of our complex frequency S, and the y-axis corresponds to j omega, the imaginary part of our complex frequency S. So let's start by looking at what happens if we have a pole that is negative and real. So for a negative real pole, our response is going to be that of an exponentially decaying transfer function. So we have stability because it is trending towards some finite value. On the opposite end of the spectrum, quite literally, is a positive real pole, which corresponds to an exponentially growing signal. Problematic. Now, an exponentially growing signal mathematically will never reach a maximum value. In a practical system, specifically an electronic system, it's going to go towards the power supply voltage. Okay, so effectively it's going to swing towards VCC plus or ground in our systems because we've designed a single supply op amp. But if we had chosen instead of ground VCC minus, it would swing towards that depending on the conditions. All right. We could also have the case where we have complex conjugate imaginary poles. So in this case, because our frequency is on the vertical axis, this is going to correspond to oscillation. Okay. Literally how we make oscillator circuits. We actually talked about this to some extent way back in circuits too. Okay. And then we can have complex conjugate poles in the left-hand plane, which are indicative of effectively a exponential decay that rings. So it has some exponentially decayed envelope. Same thing over here. And if we have complex conjugate poles in the right-hand plane, instead of seeing exponential decay, we wind up getting exponential growth that rings. Can't draw the exponential growth or decay while ringing particularly well, but I think you guys have all got the gist of it, okay? So systems whose poles occur on the left-hand side of this graph are stable, because even if we have instability, which is evidenced by ringing, so if we have complex conjugate poles, it's trending towards some finite value. So it still behaves as a stable system. For our poles on the imaginary axis, we have marginal stability, which mathematically is perfectly fine, okay? The output of the system is bounded. Nothing bad is going to happen. We literally generate oscillation from a DC response, okay? Practically, this is actually quite bad. The reason why it's quite bad in a practical sense is because things like process variations, power supply ripple, perturbing your system in any small way can actually push you over into instability where no input signal or thermal noise is capable of generating oscillations. So if you design a marginally stable system, what you will likely observe is that you have intermittent periods of oscillation that are a real pain in the ass to troubleshoot, because you can't tell why they're happening because they are intermittent, non-periodic by their very nature. And then obviously, if you design a system with poles on the right-hand side, it's just astable, right? You have designed a system that is meant to go towards the supply rail in one way or another, which for things like
astable multivibrator.
Exactly right, an astable multivibrator circuit. That's literally what I was trying to think of when we talked about that. I think we covered that in circuits too for all of you guys using an op amp based design. The The purpose there is literally, you have no input signal and yet you get out an oscillation, okay? So noise is capable of sustaining oscillation in perpetuity, okay? So we are going to relate our system stability to our Bode plots, which is what I'm more comfortable with, by employing the Nyquist stability criteria. So the Nyquist stability criteria effectively says the system is considered stable if at the frequency at which the loop gain magnitude reaches unity. So effectively, whenever our closed loop gain is 1, our system is considered stable if at this particular frequency the phase shift is less than 180 degrees. Okay. So under this condition, we have a stable system. Now, this stability is in some respects quantifiable, okay? And so what I mean by that is we have a region that is, well, not really a region, a specific point that is the verge of instability. So if our loop gain or our gain with feedback is 1 at the exact same frequency that our phase angle or our phase hits 180 degrees, that corresponds to one of these two poles, okay? Or really both of those poles because they're a complex conjugate pair, okay? We would never want to design our system to be at that specific operating point because it's too easy to push it into instability by things that are outside of our control.
Marginal stability.
Exactly right. So what we are going to do is we are going to introduce 2 interrelated concepts, gain margin and phase margin, to give us a way to better evaluate what the degree of stability that we have. So effectively, we want either the gain margin or the phase margin, and it's literally impossible to have them not be positive at the same time or not be negative at the same time. So as long as one of these meets the criteria, both of them have to meet the criteria, okay? So quantify the stability of our system. Put this down. We look at the gain margin and or phase margin of our system. And both of these quantities can be read off of a Bode plot. So I am going to draw a frequency response plot over here on the right-hand side, and then I am going to define our gain margin and phase margin quantity. So let's say that the vertical axis here represents our gain with feedback measured in decibels. This axis is the log of frequency. And let's say that this point represents 0 decibels. I'm going to extend a line over here like so. And down here, I'm going to do my phase diagram. So this is the log of omega, 0 degrees, negative 45, negative 90, negative 135, negative 180, negative 225, etc. Okay. All right, so just going to draw a frequency response diagram, and then we'll interpret as we see fit. So here we have a multipole response. We can delineate that by the fact that the slope changes. Okay. So let's observe some things here. So let's say, just for the sake of argument, that in this case, at our first pole frequency, we're supposed to hit negative 45 degrees. And let's say that we have 2 poles very close together at that second pole frequency, so that we should be hitting somewhere in the ballpark of negative 225 degrees here. So our response is going to look something like this. Probably actually should be more like that. Would be a more realistic looking ish thing here. Okay. I'm going to identify some key frequencies. Trying to get those lined up. So let's call this frequency omega 180. So that is the frequency at which our phase hits 180 degrees. And omega t is the frequency at which our gain hits 0 decibels. Okay. So our gain margin or GM is defined to be the difference in gain between the unity gain frequency omega t and the frequency at which the phase shift hits 180 degrees, which I have labeled as omega 180. Okay. So effectively, let's do this in green. We have some gain level here that is 0 decibels. And then some gain level here that occurs at omega is equal to 180 degrees. This difference is our gain margin. In this particular case, our gain margin is negative because it's the gain at omega t minus the gain at omega 180. A negative gain margin is bad because it means we have an unstable system. We have not met our Nyquist criteria, right? Nyquist stability criteria says we need our loop gain to be 1 or smaller before we hit 180 degrees, and we did not do that in this particular graph. So this is bad. Okay. Our phase margin or PM is defined as the difference in phase shift between our unity gain frequency omega t and 180 degrees. So our phase margin, let's do this in this weird sickly color green for no apparent reason. That's going to be this quantity. It is also going to be negative because we hit a value less than or more negative than 100 negative 180 degrees when we hit a gain of 1. These two quantities are directly related. So if one of them is negative, the other one has to be negative. If one of them is positive, the other one has to be positive. So effectively, if one of them meets the Nyquist criterion, both of them meet the Nyquist criterion, okay? So If we want to avoid unstable systems or marginally stable systems, we need our phase margin and our gain margin quantities to be greater than 1. How much greater than 1, measured in degrees for phase margin or decibels in gain margin, quantifies how stable our system is or how hard it is to push it to a point of instability. Typically, we want our gain margin to be greater than or equal to 10 decibels and or our phase margin to be greater than or equal to 45 degrees. So these effectively are the criterion that will guarantee a stable system, because it would require a very large perturbation to push us out of this operating point. So what we are going to talk about on Friday's class, hopefully I'll have it wrapped up in roughly half an hour or so, is what do we do if the system we have designed does not meet these criteria? And that is called frequency compensation.